Hello friends, I welcome you in lecture number 4 on two-dimensional random variables. From last 2 or 3 lectures, we are discussing two-dimensional discrete random variables, and we have discussed how to obtain joint probability distribution of two-dimensional discrete random variables. So in this lecture also, we are going to discuss one question on how to determine joint probability distribution of two-dimensional discrete random variables. So let's start with these questions. Suppose that 3 balls are randomly selected from an urn containing 3 red, 4 white and 5 blue balls. So here the random experiment is to select 3 balls out of 3 red, 4 white and 5 blue, that is total 12. So the random experiment is to select 3 balls randomly out of this total 12 balls, in which there are 3 red, 4 white and 5 blue balls. Now random variables capital X and capital Y are defined in this way. Capital X is the number of red balls chosen out of these 3 balls. So we are going to select 3 balls out of total 12 balls, and out of those 3 selected balls, X denotes the number of red balls chosen and random variable Y denotes the number of white balls chosen. And with these definitions of capital X and Y, we have to determine the joint probability distribution of X and Y. Also we have to determine the marginal probability distributions of capital X and Y. So first we will determine the range of these two variables X and Y, and then we will see what is the range of two-dimensional random variable, and then we will find out joint probability distribution. Before that, first we write the random experiment is to select 3 balls out of 3 red plus 4 white plus 5 equal to total 12 balls. So we have to select 3 balls randomly out of 12 balls. So this task can be done in 12C3 ways. So the total number of outcomes in the sample space of this random experiment is 12C3. We can select 3 balls out of 12 balls in 12C3 ways, and if you find out this 12C3, it will be 220. Now the random variables X and Y are given as capital X is the number of red balls chosen out of these 3 balls, and since there are 3 red balls, the possibility of number of red balls is 0, 1, 2 and 3. So range of random variable X is Rx equal to set containing 0, 1, 2 and 3, because we are going to select 3 balls out of 12 balls. Now among those 3 selected balls, there may be 0 red ball, 1 red ball, 2 red ball or 3 red balls. So the possible values of random variable capital X are 0, 1, 2 and 3. Similarly, random variable Y is defined as the number of white balls chosen. That is, out of these 3 balls, the number of white balls defines the random variable Y. Now there are total 4 white balls and we are selecting 3 balls. So the possible values of white balls chosen are again 0, 1, 2 and 3. Out of those 3 selected balls, there may be 0 white ball, 1 white ball, 2 white ball or 3 white balls. So range of Y is also set having this 0, 1, 2 and 3. Now we know that range of bivariate random variable ordered pair XY is denoted by R suffix XY, and it is subset of Cartesian product of range of X and range of Y. So if we take Cartesian product of these two sets, then we have there are 4 elements in this set and there are 4 elements in this set. So we have total 16 ordered pairs in the range of Rx in the Cartesian product of range of x and y. So this we can write in this way. First we fix 0 and we take this type of order pair 0 0. Then we consider 0 with 1. So we have 0 1, then 0 2 and 0 3. Similarly, we can fix 1 and we consider 1 with 0 1 2 3. So 1 0 1 1, 1 2 1 3. Similarly, 2 0 2 1 2 2 2 3 and 3 0 3 1 3 2 and 3 3. So this is the Cartesian product of Rx and Ry, and the range of bivariate random variable is subset of this Cartesian product. So we have to find out value of joint probability mass function of bivariate random variable x y at each of these ordered pairs. So first we decide the value of joint PMF at all of these points. So we know that joint probability mass function of two discrete random variables x and y is given by Pxy equal to probability of the event capital X equal to small x and capital Y equal to small y, where this order pair xy is in the Cartesian product of Rx and Ry. So now first pair is this 0 0. So this means we have to find out probability of x equal to 0 and y equal to 0. X denotes the number of red balls, y denotes the number of white balls. So here this event corresponds to the event that there is no red ball and no white ball out of 3 selected balls. So there is no red and no white out of these 3 selected balls. So in this we have no red ball, no white ball. So all the 3 balls selected must be out of 5 blue balls. So outcomes in favor of this event that there is no red and no white balls will be, we have to select 3 balls out of 5 blue balls. So number of outcomes in favor of this event x equal to 0 and y equal to 0 will be 5C3, because we are selecting 3 balls out of 12 balls. Now there are no red balls and no white balls, so all the 3 balls must come from 5 blue balls. So number of outcomes in favor of this event are 5C3 and total number of outcomes are 12C3. So value of joint probability mass function at order pair 0 0 will be equal to probability of the event x equal to 0 and y equal to 0, and it is equal to 5C3 divided by 12C3, and after simplifying we obtain 10 divided by 220. So in this way we have to find out value of joint probability mass function at each of these pairs. Now second pair is order pair 0 1. So for that order pair 0 1 means there is no red ball and there is one white ball. Order pair 0 1 means capital X takes the value 0 and capital Y takes the value 1. So out of 3 selected balls there is no red ball and there is one white ball. So there are total 4 white balls. So we can select one white ball out of 4 white balls in 4C1 ways, and remaining 2 balls must be blue because there is no red ball and there is only one white ball. So one white ball is coming from these 4 white balls and 2 remaining balls must be blue because there is no red ball. So outcomes in favor of this event, total number of outcomes in favor of this event are 4C1 times 5C2. So probability of capital X equal to 0 and capital Y equal to 1 is equal to 4C1 times 5C2 divided by 12C3, and after simplifying this probability turns out to be 40 divided by 220. And next pair is 0, 2. So if we want to decide the outcomes in favor of this event, X equal to 0 and Y equal to 2. So X equal to 0 means there is no red ball, Y equal to 0 means there are 2 white balls, and total white balls are 4. So 2 white balls can be chosen in 4C2 ways, and 1 white ball must come from 5 blue balls because there is no red ball here. So outcomes in favor of this event are 4C2 times 5C1. So P of 0, 2 will be equal to probability of the event X equal to 0 and Y equal to 2, and it is 4C2 times 5C1 divided by 12C3, that is 30 divided by 220. Next pair is P of 0, 3. That is probability that capital X equal to 0 and Y equal to 3. That is, there is no red ball and there are 3 white balls. So all the selected balls are white balls. So we can select 3 white balls out of 4 white balls in 4C3 ways. So P of 0, 3 will be equal to probability of X equal to 0, Y equal to 3, that is 4C3 divided by 12C3, and it turns out to be 4 divided by 220. So in this way we have to calculate value of joint PMF at each of these points. Suppose we are interested in the value of joint PMF at this point, P of 1, 0, then capital X is 1, capital Y takes the value 0. P of 1, 0 means probability of the event X equal to 1 and Y equal to 0. So X equal to 1 means we have to select 1 red ball out of 3 red balls, so that we can do in 3C1 ways, and there is no white ball because capital Y is 0. So remaining 2 balls must come from total 5 blue balls. So X equal to 1 and Y equal to 0. Outcomes in favor of these events are 3C1 into 5C2. So that we have written here probability of 1, 0 equal to probability that X equal to 1, Y equal to 0. X equal to 1 means 1 red ball out of 3 red balls. Y is 0, so there is no white ball, so 2 remaining balls must come from 5 blue balls, and after simplifying we obtain 30 divided by 220. Then probability of P of 1, 1, joint probability mass function at point 1, 1 will be equal to probability of 1 red ball and 1 white ball. So we have to select 3 balls. So 1 ball is red, so that we can select in 3C1 ways. 1 ball is white, so that we can select in 4C1 ways, and the remaining ball must come from 5 blue balls, that we can do in 5C1 ways. So 3 into 4 into 5 divided by 220, that is 60 divided by 220. Similarly we can find out remaining values of joint probability mass function. P of 1, 2 means probability of 1 red ball and 2 white balls. 1 red ball can be selected in 3C1 ways. 2 white balls can be selected in 4C2 ways, and we obtain this value 18 divided by 220 after simplification. Next probability is probability of 1 red ball and 3 white balls, but we are selecting only 3 balls. Random experiment is to select 3 balls out of 12 balls. So if we consider this event, then this event is to select one red ball and 3 white balls. So that is to select 4 balls, but our random experiment is for selecting 3 balls only. So this event is not possible. So value of this probability is 0. The probability of impossible event is 0. So value of probability mass function at order pair 1, 3 is 0. Then we have to find out value of joint PMF at order pair 2, 0. It corresponds to 2 red balls and 0 white ball. 2 red balls can be selected out of 3 red balls in 3C2 ways, and Y is 0, so there is no white ball, and 2 are red, so 1 must be blue, so that can be selected in 5C1 ways. So after simplifying we obtain 15 divided by 220. Then P of 2, 1, that is probability of 2 red balls and 1 white ball. 2 red balls can be selected in 3C2 ways. 1 white ball can be selected in 4C1 ways. And we obtain 12 divided by 220 as the value of joint PMF at point 21. Then probability of 2 red balls and 2 white balls, that is probability of 4 balls. So that is not possible because we are selecting only 3 balls. So this is impossible event. So probability of this impossible event is 0. Therefore value of joint probability mass function at order pair 2, 2 is 0. Similarly, the value of joint PMF at 2, 3 will be equal to probability of 2 red balls and 3 white balls, but this is also not possible because we are selecting 3 balls, so this is also 0. And then we come at this value P of 3, 0, that is probability of 3 red balls and 0 white ball. So 3 red balls can be selected in 3C3 ways, and we obtain 1 over 220. Then if we consider this order pairs 3, 1, 3, 2, 3, 3, 3, 1 means we have to select 3 red and 1 white ball, so that is total 4 balls, so that is also impossible event. Similarly x equal to 3 and y equal to 2 is also not possible, and x equal to 3 and y equal to 3 is also impossible event. So value of joint PMF at all these points is 0. So in this way we can calculate value of joint probability mass function at each of these points in this set. Now joint probability distribution is listing all these values in the form of rectangular table, and we are able to write down joint probability distribution of x and y, which is in this table. So we have written values of x in rows. This corresponds to, first row corresponds to x equal to 0, this is for x equal to 1, 2 and 3, and the values of variable y are written in this column. Column 1 corresponds to small y equal to 0, then column 2 for y equal to 1, 3 and 4 for y equal to 2 and 3 respectively. So this first value corresponds to value of joint probability mass function at 0, 0. So that we have obtained here. So we write down all these possible values. P of 0, 0 is 10 divided by 220. So that we have written here. So in this way we have written all these joint probability mass function values. This corresponds to value of joint PMF at order pair 0, 1. This is value of joint PMF at order pair 0, 2, and this is for 0, 3. Similarly, if we consider this value, then here x is 2 and y is 1. So it is value of joint PMF at order pair 2, 1. So we have written all these values of joint probability mass function in the form of table, and we are able to determine the joint probability distribution of given two random variables x and y. Now we have to determine marginal probability distributions of random variables x and y. So we know that if we are interested in the probability distribution of random variable x, then we know that this is by definition sum of values of joint PMF for which this small x is fixed, and we are summing over all possible values of y, and this we have to decide for each value of x. For example, if we are interested in the value of probability mass function of random variable x at x equal to 0, then we have to sum all these values which are in the first row. For example, if I can write here, this is equal to sigma p of x is fixed here, and I vary y, and y runs from 0 to 3. That means I am summing all these values, p of 0 0 plus p of 0 1 plus p of 0 2 and p of 0 3. That means I am summing the values of joint probability mass function in the first row. So this is p of 0 0, this is p of 0 1, 0 2 and 0 3. So if I sum all these values, I will obtain 84 by 220. So that is the value of marginal distribution of random variable x at x equal to 0. So this is nothing but, this value is nothing but value of probability mass function of random variable x at x equal to 0. Similarly, if we sum all the probabilities in second row, we obtain this value 108 by 220. So that is nothing but value of marginal distribution or marginal probability function of x at x equal to 1. Okay, so I have written here, this column corresponds to probability that capital X equal to small x. So this is probability that capital X equal to 0, that is value of value of marginal probability function of random variable x at 0. Similarly, this is probability that x equal to 1, which is nothing but p of 1 for random variable x. Same thing if we consider total in the third row, that is in the row corresponding to x equal to 2, we obtain value of probability mass function of random variable x at x equal to 2, and this is probability mass function of random variable x at x equal to 3. So if we are interested in the marginal probability mass function of random variable x, then row totals will give us the values of marginal probability function of random variable x. So this first row total is value of probability mass function of x at x equal to 0. Second row total is value of probability mass function of x at x equal to 1, and so on. Now same thing for marginal probability function of y. Suppose we change here, instead of small x, suppose we are interested in the marginal probability mass function of random variable y, then we fix y here and we take summation for all possible values of x. So if we consider y equal to 0 here, then we have p of x 0 and x is from 0 to 3. That is, if we are interested in the value of probability mass function of y at 0, then we have to sum all this probability. P of 1 0, that is this probability, this is p of 0 0, this is p of 1 1, this is p of 2 1, 2 0, sorry I made a mistake, this first one is P of 0 0, y is fixed here, so this first one is P of 0 0, second one is P of 1 0, third one is P of 2 0, and this is P of 3 0. So here value of y is fixed. In order pair xy, we have y equal to 0 and we are varying x here. X is 0, 1, 2 and 3. So this column total will give us the value of probability mass function of y at small y equal to 0. Similarly, probability mass function of y at y equal to 1 will be equal to, we have to fix y here, so P of 0 1 plus P of 0, this is first is 0 0, then 0 1, then P of 0 2, and here y is fixed, so we have to consider, here again I made a mistake, sorry for that. Y is 1 here, so here we fix y. Second component is fixed, P of 1 and P of 1 and P of 1. Y is fixed here and we have to vary x. So x can vary from 0, 1, 2 and 3. So all these values are nothing but values in the column corresponding to y equal to 1. This first one is P of 0, 1. This is P. This first one is P of 0, 1. This is P of 1, 1. This is P of 2, 1 and P of 2, 3. P of 3, 1. So if we add values in the column corresponding to y equal to 1, we obtain value of probability mass function of y at y equal to 1. Similarly, if we add the values in the column corresponding to small y equal to 2, we obtain value of probability mass function of y at 2, and this is value of probability mass function of y at y equal to 3. So column totals will give us values of marginal probability mass function at particular value of x or y. So we have written that marginal probability mass function of x is, if we add the values in the row corresponding to x equal to 0, we have 84 by 220. This is for x equal to 0. This is for x equal to 1. This is for x equal to 2, 27 by 220, and this is for x equal to 3. So we have written all these values here. Value of probability mass function of random variable x at x equal to 1, at x equal to 2 and x at x equal to 3 and 0 otherwise. So this value of probability mass function of capital X at x equal to 0, this value corresponds to the total in the row corresponding to x equal to 0. This value corresponds to the row total in the row corresponding to x equal to 1, and similarly for x equal to 2 and x equal to 3 we have these values. Same thing for marginal probability mass function of random variable y. So this first value corresponds to the total in the column corresponding to y equal to 0. This second value corresponds to the total in the column corresponding to y equal to 1. And if we add the values in the column corresponding to y equal to 2, we obtain this value, and for y equal to 3, column total is 4 by 220. So if we are writing our joint probability distribution in this way, that rows are corresponding to values of x and columns are corresponding to values of y, then row totals will give us values of marginal probability mass function of random variable x, and column totals will give us values of marginal probability mass function of random variable y. Now suppose you are writing your joint probability distribution in this way. Instead of x here, suppose you write x here and y here, then situation will change. Column totals will give you the marginal probability mass function of x, and row total will give you the marginal probability mass function of y. So be careful. If you are writing x values in row, then row total will give us marginal probability mass function of x, and if we are writing y in a column, then column totals will give us marginal probability mass function of y, and if we interchange, then row totals will give us p of y and column totals will give us p of x. So this is all about this problem. In this problem we have obtained joint probability mass function of bivariate random variable, and using the values of joint probability mass function we are able to write joint probability distribution in the form of table, and using row sum and column sum we are able to decide the marginal probability distributions of random variable capital X and Y. So this is all about this lecture. I hope you like it. Thanks for watching.